In this video, we're going to look at Unit 1 matrices, Section 9.2, Consistent and Inconsistent Systems in 3 Variables. Now, in our last video, we looked at Section 9.1, where we started off with system of linear equations in 2 variables, and we looked at 2 equations with 2 variables, x and y, and we saw that if you had a linear equation, you could graph it as a line, and the point at which the 2 graphs intersected would be the x and y solution that would satisfy both the linear equations in 2 variables. And we know that when we're dealing with systems of linear equations in 2 variables, we sometimes can have one solution, we can sometimes have no solution, or we can have infinite solutions. So we say that if you have a system of equations that are inconsistent, that means that there are no solutions. And when we're talking about linear equations in 2 variables, that would be a situation in which you would have 2 lines that don't intersect. So 2 lines that don't intersect do not have an x and y solution that satisfies both of the equations. So this is an inconsistent system of linear equations. Now, if you do have an x and y value that satisfies both equations, then that's a system of linear equations that are consistent. That means that they do have a solution. If they intersect, if the 2 lines intersect in one place, that's called an independent, consistent system because there's one solution. If you have a linear system of linear equations where the 2 equations graph the same line, that means all along this line you're going to have x and y that satisfies both equations. So when you have infinite solutions, that's going to be a consistent system that is dependent. So with a system of linear equations in 2 variables, you have inconsistent systems with no solutions, you have consistent systems with solutions. An independent system has one solution, whereas a dependent system has infinite solutions because the 2 lines graph on top of each other. So in 9.2, we are again looking at systems of linear equations, but instead of being in 2 variables, we're looking at equations that are in 3 variables. Now in section 9.2, we are looking at systems of equations in 3 variables, where the equations have an x value, a y value, and a z value. And whenever you have a system of equations in 3 variables, you usually have 3 equations. So we have something that looks like this: 2x plus y plus 2z equals 18, x minus y plus 2z equals 9, and x plus 2y minus z equals 6. So we have 3 equations, 3 variables, x, y, and z in this system of equations. And whenever you have 3 variables in an equation, on a graph that creates a plane, and you can see the planes here. It's a plane of values, and the solution is where all 3 of the planes intersect. So you can see down here we have one intersection point for all of the 3 systems. So when you have an intersection point for all 3 of the equations, that's called an independent solution, where you only have one unique solution. So that's the same as when you have a systems of equations in 2 variables. You'll have a consistent system that is independent if you only have one unique solution. Now, if the planes intersect along a line and not a point, that's an example of having infinite solutions. Also, if the planes, all 3 equations graph planes that are on top of each other, that's another example of having infinite solutions. So that is a consistent, dependent system of equations with infinite solutions. If there are no solutions, it's either because the planes don't intersect at all, or one of the planes intersects two of the equations, but two of the equations don't intersect, or you'll just find that there's intersections, but they all don't intersect at one single place. And in this case, the system of equations would be called an inconsistent system and no solutions. So in section 9.2, we want to be able to identify matrices or use matrices to identify whether we're dealing with an inconsistent system or a consistent system when we're talking about a system of equations in three variables. So first of all, looking at the system or the matrix here for a system of equations, you can see that according to a Gaussian elimination, we should have ones across the diagonal because that's the row echelon form. Now, without the ones across the diagonal, what that means is that this bottom row, we're missing a 1 here at this point. That means that the third variable in the equation, often known as the z variable, does not have a solution. There is no solution to the third variable, which means that the the three equations don't have an intersection point when we graph out the planes, or it means that not all of them intersect at one point. So you might have two that intersect and one plane that does not. So this is an example of what a matrix would look like if you have an inconsistent system of equations and there's no solution. So you really want to see 3 zeros in that bottom row, and that it's equivalent to a number, but it's those 3 zeros that are really going to give you a hint that there is no variable, there's no solution to that last variable. And that final row, it could actually be anywhere. So if you had all zeros across the top row or all zeros across the middle row, that would indicate the same thing, that that variable does not have a solution for all three equations. So that was looking at inconsistent systems of linear equations of equations in three variables. Let's look at consistent systems that do have solutions. So I noticed in my videos that my pointer's not showing, so I'm going to try and do better at pointing at things by using my pen. So we're looking at consistent systems. So we are going to have solutions. Now, either we're looking at one unique solution where all three planes intersect at a single point. This is called an independent system. Or we're looking at a dependent system with infinite solutions. So that means either the three planes intersect along a line, or it means that the planes graph on top of each other. And so consistent independent systems have one unique solution. Dependent systems have infinite solutions. So it's important to be able to identify matrices that show independent systems and dependent systems and what they look like. So if you have an independent system with one unique solution, we are looking at something like this, where we have a Gauss-Jordan elimination showing, because we have ones all the way down the diagonal, zeros in the other positions, and you can see that each row maps to one single variable. So in this case, x is equal to 5, y is equal to 2, and z would be equal to 3. So there's one solution for each of the variables. So this is showing an independent system. Now, for a dependent system where you have infinite solutions, what you will notice is two things. Either you will notice that when you have row echelon form, one of the rows will have zeros all the way across. This means that we're looking at infinite many solutions. This is different from an inconsistent system where you might have zeros across, but this last column will have a number in it. It's not equal to 0. Now in this second example, down here, we have a non-square system. And a non-square system is where you only have two equations with three variables in the system instead of three equations. And this is called a non-square system. So you also need to be able to identify what that looks like in a matrice, so you can say that it is infinitely many solutions and dependent systems. So when you have a non-square system, you're going to have a system with fewer equations than variables. So you can see in this system of equations here, I do have three variables in each of the equations, but only two equations are given. So when you set up the matrice, it's going to be a non-square matrice. You're still going to want to get ones in this diagonal here. So they're showing some matrice computations to get that into row echelon form. So ones and zeros underneath the ones. But what you'll notice is that in this, in the rows, you're never going to be able to get a solution to all three of the variables. So I'm going to just get rid of my marks here. As far as we can go with this matrice is here, where we have the ones in the diagonal, the zero in that position. And that's going to translate back to these two equations. So from this matrice, we're going to write out the two equations again in a more simpler form. So we will have x plus 2y plus z and y plus 3z equals 2. And then when we go to solve for the variables, we are going to back substitute. We know that we can take this second equation, y plus 3z equals 2, and we can rearrange it so that it solves for y. Now we do have an unknown in that solve, but that's okay. And then what we're going to do is we're going to substitute that solution for y into the first equation. And then through that, we get what x is equal to with z in the variable. So you always want to have the same variables describing each of the x and the y variable. And then z will remain the same. So once you've solved for x and once you've solved for y, your solution set is going to have z as the only unknown variable, because you can't solve for z in a non-square system. So that's how you would solve for a non-square system, and this is a consistent, dependent system of equations because there are infinite solutions, because it all depends on what z is equal to. If z is equal to 1, you're going to get a whole bunch of different solutions. If you get z is equal to 2, so on and so forth, you'll get infinite solutions to that. So in section 9.2, you could get a question like this where they give you a matrice that you work out doing row computations. And when you get down to the row echelon form at the very end here, you can see that you should have diagonals across of ones here, but this last value you can't seem to transform into a zero. So you get zeros across the bottom and equal to a number that's greater than 0 or that isn't 0. And because this is not a true system, what that means is that there's no value for the z number that's going to be true for all three equations. So in this case, we're looking at a system that has no solution, and so the solution set is going to be void or an empty set. So this is an inconsistent system of equations in three variables, and there is no solution. So that's the way you would identify that there was an inconsistent system, is if you had all zeros across a row equivalent to a number that was not 0. And that gives you an idea that you don't have any value for z. And the last example I have here on this slide, you can see that we're given in a matrix that we need to solve, and we get down to the point where we have in row echelon form, but there isn't a 1 in this last position, and also we have zeros completely across the board. This is going to tell us that we have a dependent system, and that we're going to have, it's a consistent system because there is a solution. It's a dependent system where we are going to have infinitely many solutions. Now, if there was one solution, then that would be a consistent independent system, and we would be able to have something that works out across the bottom. But in this case, there'd be, so for instance, there'd be a 1 here. But when there's a 0, that tells us that that's a consistent dependent system with infinitely many solutions. And then you can solve for that solution where you have one variable still left in the solution. So this final row is telling us that our z variable is not going to be constant, and that we're going to use row 1 and row 2 to solve for our x and y in terms of z. And we're always solving x and y in terms of that unknown z value that does not come out properly in the matrix. So looking at this very first system of equation here, we're going to write that out again as in terms of y. So we have, oh, that's not the right one there. Sorry about that. If we were to write out those systems according to that matrix, I'm going to do it up here in the right. That first row of 1, 2, negative 2 and 3 becomes x plus 2y minus 2z equals 3. And then the second line would give us y minus 2z is equal to 1/2. And then what we're going to do is we're going to solve for y using that second equation. So we rearrange the equation and we get y is equal to 2z plus 1/2. And then we're going to take that and substitute it in for y here. And that's what that equation is doing there. They substituted y in, which is this 2z plus 1/2, and then they simplify to get that x is equal to negative 2z plus 2. Then we use those equations as our solution. We know that x is going to be negative 2z plus 2. We know our y variable in terms of z is 2z plus 1/2, and then our z value just stands alone. And that's how you write a solution when you have a consistent dependent system with 3 variables and infinitely many solutions. Well, that's it for 9.2, and I thank you for watching.